Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Ludmilla Kolokolova with us today. Hello, Ludmilla.
Yes, hello. Hello, Frank. Hello, everybody.
Hello, and thank you for agreeing to talk about your very awesome article, which we'll get to here. And Ludmilla, what is your geolocation? Where are you at?
Oh, this is exactly University of Maryland,
Okay.
and I'm in College Park, University of Maryland. So, Maryland.
Very good.
Yeah.
And it is July 22nd of 2025 as we record this. And how is summer doing in Maryland? Are we getting the big hot humidity yet?
Oh, it's horrible, you
It's
know.
horrible.
Yeah, it's a heat wave. I think it just hit summer with, not wave. It just the whole
Yeah.
summer is heat wave. But today it's a little bit better.
Ah,
Today the temperature is below 90, finally.
so I'm in Phoenix, and we are definitely in our summer mode. And I would be delighted if we got something below 90.
Below 90, okay. Yeah.
So yeah, we broil a little bit here in the summer. So very good. Let's see. And Ludmilla, what do you like to do for research?
Uh, well, my main fascination is with technique, not with object, with techniques. It is polarimetry. So
Uh-huh.
I love polarimetry and I try to apply it in different objects. But the most interesting results I have received for cosmic dust of different origin. It can be dust in molecular clouds, in AGNs, in protoplanetary disk, and in solar system, of course.
Cool.
And yeah, including artificially created cosmic dust. That is a
Oh, there we go.
topic
Yeah, yeah.
of my
Characterization
of
of
my article. Yeah.
yeah, yeah, yeah. Very cool. Very cool. Well, we're gonna get a little of that expertise of yours applied to Dart Ejecta here. So this is Planetary Science Journal. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Characterization of the Dart ejecta using computer modeling of the ground-based and HST photopolarimetric data. And Ludmilla, take us away.
Uh, okay, probably first I explain a little bit as a title, and then I will talk about the contributors to this research. You see, we have big kind of a group of people who contributed
Mhm.
because it's a combination of different technique.
Okay,
So we have people who did polarimetric observation, who did a photometric observation, who produced imaging, and all of these data are combined here. And then it's not the end of combination. Then computer modeling comes, it is also combined. We combine light scattering modeling of the light scattering by dust and dynamical modeling, how the dust is moving.
yes.
So it's a big, paper on a combination of different techniques including observation, different techniques, different instruments, different telescopes, whatever.
Cool.
So, who are the authors? So, the second author is a guy who did the main modeling, light scattering,
Okay.
Johannes Markkanen. So, he's a Finnish guy who currently works in Germany. So, he did light scattering modeling and dynamical modeling. So, really, his contribution is in computer modeling. Very interesting author is Quentin Ludet. This is undergraduate student whom I
Oh,
knew since he was a high school student who was
wow.
very interested in astronomy and wanted to work with me when he was in high school and
Cool.
actually created a very nice website with a database of computer modeling results.
Okay.
And yeah, this year he graduated. This was his last research that he did at the University of Maryland.
Congratulations.
And as I know, he already have a job. He did not want to go to graduate school. Also, I think he would be good, but he had some high-paid actually job already.
Nice.
Uh, Zuri Gray, also a young scientist, that she got her PhD working with the Dart ejected data. This was her main topic for her PhD thesis. She
Cool.
did the observations
Cool.
with Stefano Bagnulo, who is her advisor,
Yes.
and who also, of course, was involved in polarimetric observations that Zuri accomplished. So Zuri and Stefano, there are two polarimetric people, and now we move to photometric people, who is Cyril Opitum and Brian Murphy.
Cool.
So again, Brian, by the way, is also a graduate student. So we have a lot of young people on this
Good.
project, and Cyril is his advisor.
Very good.
So yeah,
Great shout out. Great shout out. Okay, so let's go
okay.
into it.
Okay, so well, while we are on introduction, I want to talk a little bit about the DART mission.
Please.
The DART mission was a mission to test if any asteroid will be moving toward the Earth, if you can change its trajectory, that it will not hit the Earth, but goes a little bit, in different direction. So,
Yes.
and the idea was just to bombard this asteroid with some kind of actually spacecraft
Uh-huh.
that allows it to move, to change the trajectory.
Hopefully.
For testing this idea was selected a binary asteroid. So it has a main body and a small body that rotates around. And the idea was that we hit this small satellite
Uh-huh.
and it changed its orbit around the big asteroid. And this we will be able to observe even from the Earth, because change the orbit, it change how the brightness with time will be changing, so-called light curve of this binary asteroid.
I'm with you. Cool.
It was very interesting project, because you can imagine a very small asteroid that kind of 100-meter in diameter need to be hit uh, from the Earth, should it be controlled, everything, and really get to this asteroid. But the impact was very nice, almost in the center of the asteroid. It was elliptical
Perfect.
shape. But the main, unexpected thing was that this produced a huge cloud of dust,
Yes.
eject. So, not expected, but it's appeared to be very good for the project, because we expected that it will be just, some impact that moves the orbit. But because of this ejecta, it worked, like jet propulsion. It moved asteroid even more. So it was actually
Nice.
the crucial thing, is this ejecta.
Okay.
And actually, finally, the period of orbital period of this small satellite changed 33 minutes. Also, expectation were seconds, but there were 33 minutes. And
Cool.
again, this is because of ejecta. So you can imagine that ejecta was of a big interest of all people from the DART mission and scientists in general, because they wanted to understand why this asteroid produced such a huge cloud. And our
Question?
paper was actually determined to define what were the properties of these dust particles. So why they were so, why so many particles were released during the impact. And yes, this is what we try to find out. And yeah, we found that the best way to do it is combining different observations that are kind of reflecting the properties of the dust particles.
Cool.
And this was, of course, photometry that show how bright ejector was, and polarimetry, because polarimetry, it's, as I said, my favorite technique. It
Yes.
is it is sensitive to things that no other technique sensitive, to
Yeah.
the structure and size of particles.
Correct.
And you will see later that really it allowed us to find out what with the structure and size of dust particles in the ejecta. And
Yeah.
finally, actually determine the mass of the ejecta. It was important to understand why, because it allows to reveal the momentum that this ejecta produced, and to explain why such a big change in the orbital
Orbital
period
period.
happens.
Yeah.
Yeah.
Cool. I'm with you. Nice.
Yeah, so we wanted to find again, as is the data that allows us to recover the properties of the dust particles. And of course, I thought that it would be polarimetry because
Of
that's what
course.
I
Of course.
do. Yes. But you know what is good about polarimetry? Polarimetry is actually the ratio of brightness in one plane and in the perpendicular plane.
Yes.
And this is why, because it's ratio, it depends only on the intrinsic properties of particles. Brightness depends also on number of particles. So if you just study brightness, you don't know the object is bright because
Well,
of properties of particles or because there are just many, many particles.
yeah.
Polarization is sensitive only to properties of particles.
Okay.
Because of the ratio, the number of particles goes away.
Doesn't matter. Yep.
And another characteristic that also sensitive only to properties of particles is color, because color
Yeah.
is also a ratio of brightness in one wavelength and in the other wavelengths. So we wanted to combine the data that on color, on polarization, and also I was just involved in the HST observation of dart ejecta, and I
Oh,
said, okay, we have an image of ejecta.
nice.
So let's, when we have properties of particle, try to interpret what we see in the image of the ejecta. And actually, the next will, yeah, no, I want to also to mention what this table one tells us. The
Oh,
table
yeah.
one, it's yeah, here, it shows all dates of observation from all our sources of information used. It is a photometric or spectro, actually, spectrophotometric
Yeah.
camera on very large telescope, VLT.
Mm,
And force
good
2 is
tree.
photopolarimetric camera on VLT also.
Mhm.
And WFC3, it's a camera on Hubble telescope, and we had data from this camera.
Yes.
Because the ejecta, were moving very fast, situation that we observe changed every day. This is why also, so many observations were accomplished. We were looking among them for observations that
Well
were
timed.
done at the same day, that
Yes.
we have photometry, polarimetry, and imaging on the same day. And unfortunately, again, I say so many observations, we found only one day when these observations
Take
were
it.
done and all instruments, and it was October 4. The impact itself happened on September 26th. So you can see
Okay.
it was like 7
Okay.
days, I think, after
Hmm.
impact, or 8
Hmm.
days after impact. And
Very cool.
this is the date, this is the date, and for a Hubble telescope, yeah, this
Yep.
is the date. It was 5, but it was very close to the times it was the observation on October 4 were
Nice.
accomplished. So we have, unfortunately, we wanted to study how things developed this time, but we had only one day when we had observation for all three instruments. Okay, and now we
Better
can
one than zero.
uh, go to what our observations showed us, to the
Okay.
figure that is figure 1 in this paper.
Okay. Figure one.
Oh,
You want to do table
uh,
two, or
well,
we can wait. We can come back.
yeah, probably.
Okay.
Yeah, we need to come back to this table later.
Okay.
Okay, so these are the data. The polarization in two filters, in blue and red,
Okay.
color,
Okay.
oh, actually
You
also two
know.
filters, G and R, but it's close to what we saw in polarization. And
Okay.
finally, WFC cameras, it has actually quite broadband, filter. So
Yes.
we could not really say it's specific filter. So what I wanted to say here, you can see that polarization, of course, unfortunately, I know many people don't like polarization because it's very sensitive to, how bright is the object. It changes a little bit, and polarization can change
Oh,
dramatically
sure.
because it's ratio of two brightnesses. So here is a polarization in a blue filter, and usually it's always in red filter. Polarization is more stable. Actually, I don't know why, but we always get better data in red filter. Uh, anyway, polarization, uh, you can see it is not really changing with the distance. So this is distance from, yes, so actually this
Uh-huh.
shows actually the picture, but in numbers. So polarization, how it changed with the distance from
Gotcha.
the impact. And you can see that even so we have more noisy data in blue filter and then in red filter, we
Yes.
cannot say we see any change in polarization. It's the same along the whole ejecta, this plume that we observe.
Yes.
Uh, the same actually with the color. In the beginning, we
Mhm.
see some change, but this is very close to the asteroid. But then we
Good one.
see no change. The
Pretty cool.
color is not changing
I'm
as
with
we go, up to 1,000 kilometers from the asteroid, and we see
still the same.
the same characteristics. So uh, and finally, the image that we have as
Pretty.
a result of our HST observation. Of course, here, because image, again, I say, depends on the number of particles. Number of particles changing as we move out of asteroid, and this way brightness changing.
Uh-huh. Okay.
So yeah, these are, our starting point.
Okay.
So this what we got for October 4th, I said, and our idea was to model this polarization, color, and finally the HST images.
Nice.
Uh, what is important here for our modeling, what appeared to be important, because we had polarization in two filters, it shows that in the blue filter, the short wavelength, polarization was higher.
Yes.
In red filter, it was lower.
Little lower. 6 versus
And
5.
this is actually, you think, so what? It's very important because we knew that solid particles usually show this, but for example, in cometary atmospheres or in debris disk where we see aggregated particle, it's
Yes.
opposite. Usually in red filter, polarization is higher than in the
Okay.
blue filter. And this is why, we immediately had some limitation. These particles are not like in comets, and these particles are different from debris disks. And then later you will see what was our conclusion, what the particles are. That's why I say polarization gives us idea about structure of particles, and we already see it here,
Yep.
already from this images.
Fascinating. Very good.
Okay,
Okay, I'm with
so
you.
yeah, so the next thing was to model this data to reproduce correct polarization, not changing with the distance, correct color. And it's a little bit above. Dynamical modeling was our last step. Before it's light scattering modeling.
Ah, here we go. Okay.
Unfortunately, the paper was kind of structured not in a very convenient way.
Okay.
So that's why the observational data are later than discussing of the modeling. So light scattering modeling
Okay.
was done, as I said, Johannes Markkanen. And to make this modeling really trustful, we had to use the data not only for October 4. So that's why if you return to table 2, that was, yeah, here. We used the data for other dates. You
Yes.
can see for earlier and later dates, because
Yes.
we wanted to see, to model one point, you never get any
I can fit a lot of lines per
reasonable
point.
result. So we wanted to see if polarizations that we model, it's consistent with other
Okay.
observation. And this is why we modeled polarization and color for several dates.
Okay.
And
Hmm.
uh, I'm thinking now, yeah, we probably can move to the next figure that shows results of the
Right.
observations.
Modelings.
It's figure
Cross
2, I
two.
think.
Yep. Yep. Let me slow
Yeah.
down. And ooh, here we go. Model
Yeah, it's a
XR.
huge figure
All good.
because we did a lot of computations trying to understand what these particles are were. And I can say that it was not easy because we tried different structure of particle, we tried different size of particle, and we could not find the combination of the characteristic of particle that can reproduce what we observe for dart. For
Ooh.
example, on the right part or right side of this figure,
Hmm.
you see our modeling that we accomplished for solid particles. We just saw, okay, because
Okay.
the blue polarization, as I said, was higher, than red.
Yes.
We said,
Yes.
oh, probably particles are solid.
Okay.
And we did computations for, a set of sizes of particles. For this type of particles that's shown in the medium, figure, this image. It
Yes.
was irregular particle, but it was solid irregular particle.
Okay.
And we found that only one size of particle probably can reproduce the observed polarization for, several phase angles that we observed.
About
And
40.
we knew already from other observers that there was a very broad size distribution that included small particles and large particles. So it could not be just one size. And this is why we continue, experimenting with different structure of particles. And finally, we found that particles that are shown on the left and on the, again, like a middle, yeah, this panel,
Uh-huh.
this type of particle can reproduce the observation. You can see polarization actually for all size of this type of particle is the
Yeah.
same.
Yeah.
So yeah, this
Yeah.
means that if you see this tail or that, along the tail, don't see change in polarization. Yeah, if even the size of particle changing, yeah, we don't see it because it's the same for different sizes.
Okay.
It showed exactly what we wanted. Blue polarization was
Elevated.
higher than red polarization,
Cool.
and actually good. The results were good for the color too.
Good.
So yeah, what is this particle? It looks a little bit strange. It's aggregate, but not like in cometary dust. It's aggregate of submicron particle. In this case, it's aggregate of 10 micron
10
particles.
micron particles. Okay. Hmm.
Yeah, and what
Oh,
this figure shows, I don't know if you can increase that people can see the particle itself, in more detail. Oh, yes, good. So, yeah, the particle. So the particle consists of 10 micron irregular
chunks.
particles. So each of
Okay.
these particles is also irregular. And it appeared to be we needed quite a compact particle. The porosity here is 55%.
Okay.
So you probably heard about other particles like a cometary or others. They have porosities like 90%, even
Yes.
95%. Here, 55%.
Oh,
So compact aggregate. This what we found, what this particle
cool.
are. That actually very well consistent with the idea that Dimorphos asteroid is so-called a rubble pile.
Yes. Yes.
It's actually
Yeah, the little ones.
kind of yeah, rubble pile is a good definition.
Yeah,
It's
yeah.
a mixture particle of
Oh,
different size and
okay.
quite kind of also I would say porous in meaning that it's not solid.
Yes, yes, I'm with
Okay,
you. All right.
so if you open now the whole figure, so our next step was to combine all of this data uh, and recover the size distribution of particles that produce the right uh,
Polarization.
polarization, blue, red, and right color.
Yes.
So actually, this work was done by this guy, Quentin, the undergraduate student. He
Nice.
found the size distribution, and this size distribution was determined to be 3.3, that actually very nicely described behavior of polarization and of color.
Okay, cool.
So this was not the end of the modeling, because the idea then came that, well, um, I would really, if possible, to come back to the figure one to see
Sure.
our
Absolutely.
observational data.
Let's go back to
Uh,
figure one. Oops, I lost it there. Hold
yeah,
on one sec. Figure one. There we go.
yes, yes. So uh, the particles are moving from asteroid and go through this ejecta, and the particles uh, of different size move with different velocity.
Yes. Okay.
So
hmm
we can expect different size of particles in the beginning of this,
Cool.
image on the left
Yes.
and at the end.
Yes.
And this is why we decided to go with dynamical modeling and
Okay.
see how this size of particle change. And here we can go to figure 3.
Okay.
Yes.
One, I'm with you. Figure one, figure two, and figure three on the size distribution. Woohoo!
Yeah, yeah. So here the dynamical modeling was done that consider, what we usually consider when we model
Okay.
dynamics of dust. We consider gravitation of asteroid, of the
Oh,
sun. We consider radiation pressure. That is very important in this
oh yeah.
case.
Oh
And
yeah.
actually, this why it moved the particle to this elongated feature to the tail.
hmm
And this was done. I don't know if people want to see the formula. It is a
Sure.
little bit above. So, uh,
Let's see. Here we got
yeah, this formula that shows, yes, we consider gravitation. It's the first term. No, first term, sorry, it's radiative pressure. And
of
we consider gravitation. It's the second term.
course.
And yeah, we
Okay.
modeled how these specific particles, these aggregates, compact aggregate, how they move under these two forces. Actually, here also this, the radiative pressure was determined based on aggregate structure. So how radiation interacts with particle depend on its aggregative structure. If it was
Yes.
solid particle, it could be different.
I'm with you.
Okay, and
I'm with
now we can go to figure 3
you. Okay.
and to show the result of dynamical modeling. So
Right.
what it shows that at the moment of our observation, October 4, uh, yeah, this is a distance from the asteroid. This is the size of particles.
Uh-huh.
So
Uh-huh.
uh, uh,
So,
only the most distant part of the asteroid, that is left up corner, only very small particle could reach it. We
yes.
can see, only this particle. But as we move to kind of closer to asteroid, larger and larger particle could reach these distances. And
Yes.
finally, near the asteroid can be a particle of millimeter size even. So this was one more kind of limitation in our description of the ejecta. So we knew the structure of particle, we knew size distribution, we knew the limiting size as a change with the distance from asteroid.
Right.
And already with this data in hand, we could move to modeling the HST images.
Cool.
So our data already consistent with color, with polarization, with dynamical properties, and now we model images that were also in figure 1.
Yeah.
And you can see that
Just want to refresh
yeah,
the memory on
yeah, yeah. Let's see it
color.
again.
Yep.
Let's see it again. So you can see that the brightness of the ejecta, yes, it changed quite significantly with the distance. And again, I say this is because different type of particles and different number of particles reached different distances.
Yes.
Okay, and now if you go to our modeling results, so it's figure 4.
Let's go to figure 4.
Oh, we already, yeah, it was, yeah, right here. So again, I say with this information in hand, we started modeling column density. So here is formula how we did it. It's a kind of a very simple thing. Can you show a little bit
Let me,
up? Yeah, yeah.
here we go.
We just consider brightness in each pixel, and the brightness that we modeled for our size distribution, our range of sizes of particles, because light scattering modeling gives us the brightness. And this gave us the number of particles at each pixel of HST observation.
Got it.
And then when we knew number of particles, of course, if you now go a little bit up, I think it is
You can get a mass.
yeah, we can get the mass. Yeah,
Mm-hmm.
yeah. Again, based on our model of particle and size of particles and size distribution, we can model the mass of the dust and how it change with the distance
5
from
kilograms.
asteroid. I can, if you go to here, you can say, well, they look very similar. Why you show, both image, both plots? They're actually different because when we calculated mass, we took into account that also kind of average uh, porosity or compactness of the
Yes.
dust particle is 55%. It is larger for smaller particles and becomes
That's why.
smaller for larger particles.
Okay.
Larger particles are always more porous than you can imagine. If you have two particles, and porosity is,
Yikes. Yikes.
zero. Yeah, and we took it into account when we calculated the mass. So the
Good.
mass of particles at each distance was different because there were particles of different sizes.
And different porosities.
Yeah, different porosity in the result, different,
Yes.
yes, different size in the result, different porosity in the result, different mass, yes.
Okay.
And so we showed how the mass of dust particles change with the distance from the asteroid, and we calculated the total mass of the ejecta. Total mass of the ejecta appeared to be, from our calculation, 10 to the power 4 kilogram.
Mm-hmm.
So,
Mm-hmm.
when I tell people about this, the people usually say, well, it's too small because from other observations, not from other observations, sorry, from modeling of the impact.
Impact. Mm-hmm.
So it's a cratering modeling. They're done by, people in Switzerland and here in the United States.
Yes.
They estimated the mass of the whole ejecta much larger, 10 to the power 7.
Ooh, that's
So
3 orders.
why we have this difference? The difference is because we consider only ejecta in the tail, but still there were some dust around the
Around the
asteroid.
object,
More,
right?
more,
Free cloud.
even more than some dust, they started getting on orbits around the main
Yeah, yeah, yeah,
asteroid
yeah,
and
yeah, yeah.
around Dima. So we expect that
Okay.
maybe still some dust stay inside this system.
Most.
And the other thing
Right.
why our mass was smaller, because the impact was not, something very short. As we know now that the dust was ejected for some time after impact. And
Interesting.
that's why, yeah, what we saw on October 4, it was not the final ejecta.
Wasn't
The
peak.
final continued developing
Yeah.
and adding mass to.
Well, that's interesting.
Yeah.
Okay.
So, but at least, yeah, this I say it was upsetting. We didn't have data for other dates. But yeah, for this date, we got this estimation of mass. So,
Cool.
what I want to say at the end of this story, it's for me, it was not only, uh, getting more details about asteroids, about cratering process, about efficiency of dart impact, but it also shows the power of combination of data
Yes.
of different techniques. So
Yes.
if you get polarization and
Makes your life.
color and images, and actually will be good also to have, let's say, data in different spectral ranges, like in UV, in
Oh,
infrared,
yeah.
then we can really find a trustful model of
What's
dark matter.
going on? Right.
Yeah.
Very cool.
Okay, so actually, I think this is
Oh, here we go.
uh, the main thing about this paper. Probably took too long. Yeah.
Very good. You got all the colors, aggregates. Very cool. Very good. Beautiful. Beautiful work. Awesome.
Yeah. So, yeah, I don't. You probably have questions, so I don't want to uh,
Okay.
interrupt you.
Okay. Very good. Cool. Ludmilla, I want to thank you so much for walking us through your very awesome article. Thank you so much.
Yeah. Thank you for yeah
Uh,
inviting me to talk about it.
Let's see, and you kind of hinted at it at a couple of places as we went on through. So let me push and ask a little bit. And where do you think we go from here, given the published article? Is there additional data, perhaps in other wavelengths that could be leveraged to improve either the distribution or the colors or something of that order? Is there additional, more sophisticated modeling that might be done? So, what do you think are the next steps on modeling the Dart ejecta? Where do we go?
Well, from kind of point of view of my studies, that I study light scattering by dust, I don't think we can do more on this because, for example, you could see the table that show the observations, how long they were done, and you could
Huh?
see that they stopped at some moment, and usually, well, not usually, but what you could see, polarimetry stopped earliest,
Yes.
then color stopped later, and HST was the longest. It is because, for polarimetry, ejecta became too faint already
Yes.
in December.
Okay.
For color, it was still okay, like in January. And HST also, of course, it was HST, it's a better telescope. HST could observe ejecta until spring, but then they also become too
Too dim.
faint.
Yep.
So no more data could be
Okay.
obtained. So
Okay.
we need to wait until, Hera mission, it's a mission that
Yes.
European Space Agency
Yes.
is preparing to go back to this binary asteroid and to see the results of
Ooh, that'll be
what
nice.
happens there. Yeah, because, unfortunately, the DART spacecraft just, it was a
Bang.
kamikaze, it just died during impact. And the other, it was
Got
a
the emails. Yeah.
CubeSat, a Lichia Cube.
Mhm.
It just passed this area very quickly. We have kind of
Yes.
couple minutes of data. So there's just not no other data, but
Okay.
we have active asteroids. We have objects in solar systems that also are asteroids, but they have tails. And this is, in some cases, it's because they have some volatile material, so they're like comets, and they have also dust lifted during the sublimation.
Yeah,
But we also have asteroids that are active due to collision. For example, asteroid Shela, yeah, it became active because of collision. So all things that we developed here can be applied to other active asteroids. And this is actually what I'm looking for, to get data from the observers. I encourage all of the people with whom I work to observe active asteroids. And yeah, then we will have more objects to model.
very cool. Very cool. Well, that'll be really exciting to see coming up in the future here, particularly with the Hera mission. I think that'll be really interesting to see what they
Oh,
find,
yeah.
what that
Yeah.
looks like. Yeah, very cool. Ludmilla, I want to thank you once more for walking us through your very lovely article. Thank you.
Thank you. Yeah.
And that will do, everyone. And I hope this made your astronomy dart day just a little bit better. And we will see you on the next one. Bye bye.
Bye.